corresponding to -1. So let me take one of these. So what we get is minus E square over Vf square minus I square K plus E over C By square minus del square del V square phi minus E over C phi plus equal to 0. So let me change the variables here. Capital Y equal to K plus E over C By, and so this can also be written as K plus Y, where in terms of the magnetic length, where LB is C over EB under root. Okay, then it is easy to see. I can write this equation in the following form. The y square plus 1/2 here E over C B square phi plus equal to 1/2 C E B square, then E square over Vf square plus E over Cb and phi, this is phi plus y, and this is an eigenvalue equation which we have E prime equal to phi plus y. This is an eigenvalue equation because this is multiplied by this phi plus c. And this you can recognize here. This is an eigenvalue equation equal to E prime phi, and this is the well-known the harmonic oscillator. This is the harmonic oscillator with the frequency here, this y square here. So this is the harmonic oscillator with the mass here minus 1/2, and this is omega square W square. Okay, so with this then you have here, so the eigenvalues you know from the harmonic oscillator. So the eigenvalues are the En prime equal to n plus 1/2 times C over Eb, just from the harmonic oscillator. If I substitute to the original variables, I have 1 over f square epsilon n square plus E over C B equal to twice n plus 1/2 times Eb over C. R epsilon n is equal to plus minus the cyclotron frequency times n, where I will put it mod n here, and then we can take n equal to 0 plus minus 1 plus minus 2. Okay, so this is usually written as sine of n, and then omega c n under root mod n under root. Okay, written in full, if I put the value of the cyclotron frequency which we have here, omega c is just twice under root Vf E over Cb under root 2 under root Vf over the magnetic length So then we have here, actually this one formula, sine n twice n and h. I put h back here, Vf square over Ce. So this is the formula for the Landau levels, which was used by Kashyap to explain the quantum Hall effect. So I have derived it in a simple way in this fashion, and you see it is different from the non-relativistic one, and because in the relativistic you always have this one here, and you have the sign also here. Now this we have done it for this is the spectrum of Landau levels. This is on the same line as you have ordinary Landau levels in quantum mechanics. And since it is a harmonic oscillator, you can also write down the wave function if you like. So these are the Landau, because I have started with psi A, so these are the Landau levels near Dirac point K prime. And there will be Landau levels at the opposite Dirac point. So the Landau levels are then actually doubly degenerate because of that. And this has been verified experimentally. Okay, so this is with the magnetic field. Let me go to the Coulomb-like problem, the other one, where I put now the magnetic field equal to 0 and take the electric field only. So I have this equation here. Okay, so this is then the Coulomb-like problem. So I will put now AI equal to 0 and magnetic field equal to 0, and since I equal to 1, 2, so we will have then EI as is minus AI delta I A naught. Okay, so we will have then E2 is equal to minus delta 2 A naught, and E1 is equal to minus delta 1 A naught, and psi A, as I have written before, psi plus psi minus, corresponding to sigma 3 plus 1, sigma 3 minus 1. And then D naught square in this case is minus E over Vf minus E over C A naught square, and this that is simply del square. Okay, so this equation which I have written now, this is 0, and this you can evaluate, will have these components here, and this is, and then you can take as Coulomb potential, it is not here. So we can proceed as we proceed for the hydrogen atom, and so let me write this as psi A equal to 1 over R 1 half chi, another wave function. Then you see we have this equation minus sigma f minus E over C A naught square 1 0 0 1 minus del square 1 0 0 1. Then we have minus IE over C 0 1 1 0 minus del 2A naught and plus IE over C 0 minus I 0 minus delta 1 A naught equal to 1 over R 1 half chi plus chi minus equal to 0. Okay, so this comes actually from these sigmas. These matrices comes from this one here. Okay, so for graphene, this E over C A naught is minus G over R minus where G is ZE square over BF epsilon, which is this is the usual constant which here in the electromagnetism. Now this equation is separable in cylindrical coordinates. For hydrogen atom you have spherical coordinates, but here we have cylindrical coordinates. That is x equal to r cosine phi, y is equal to r sine phi. Then you can write del square, which is 1 over r delta over delta r delta over delta r plus 1 over r square delta square over delta phi square, and delta 2 a naught equal to delta a naught over delta r times sine phi. This is center potential, no dependence on, so you have delta cosine phi. So then the equation actually reduces to A 1 0 0 1 plus IA 0 minus I e raised to power minus I phi I e phi 0. Then we have chi plus chi equal to 0. Where actually A here, because you have to put it this one which I introduced, this the redefinition here, yes, this one here. So if you have done that with little algebra, you will see that A is equal to delta over delta r square plus 1 over 4 1 over r square plus epsilon over f g over r square plus 1 over r square delta square over delta phi square, where A, so I have put here IA, where A is minus G over R. So now you have to diagonalize it. now first one here is the multiple of unit matrix, and the other one, so it commutes with everything. So there is the other matrix here is the one which is multiplying this one here, IA. So let me call this matrix the matrix multiplying IA. Let me call it M2. So this matrix is here is Hermitian, as you can see. So is Hermitian. And therefore we can diagonalize it by 2 by 2 matrix. Let me give you, it is a good exercise. Where U inverse is 1 over determinant U, U1 1, U2 1, U1 2, U2 2. Okay, anyway, you can write down determinant U and etc. So the diagonalization actually gives U inverse to U equal to D, the diagonal matrix, which is D is actually 1 0 0 minus 1. And U here comes out to be 1 e raised to I, e raised to power minus I phi minus I e raised to power minus I phi I e raised to power minus pi minus I e raised to power minus pi 1. And similarly you can write U inverse here, which you can easily write. So then our equation becomes, after diagonalization, A I G over R square 0 0 A plus I G over R square chi 1 chi 2 equal to 0. Actually I chi 2. Where these are then the new, after diagonalization, these are the, so chi 1, I chi 2 are actually U inverse chi plus chi minus. So you get two equations out of this, which A minus IG over R square chi 1 R phi equal to 0, and A plus IG over R square chi 2 R phi equal to 0. Now in 2 dimension, as we have seen, we have the total angular momentum is J is J3 equal to 1/2 sigma 3 plus L3, and L3 is the orbital angular momentum x1 p2 minus x2 p1, and eigenvalues of J are J equal to plus minus 1/2 plus minus 3/2 and so on.
In 2 dimensions the rotation group is SO2. So
Yes.
why would we have, I mean, that's U1, the representations are labeled by an integer. So why should we have sigma 3 over 2 there?
Because the spin here comes in actually. The spin also comes in. because we have the spin angular momentum also.
So essentially we are looking at SO2, 1.
Yes, because the spin is also. So then you can label your state by this one here, R1 R e raised to power I j minus 1 half phi and chi2 r phi equal to R2 R e raised to power I j plus 1 half phi. And then A is your delta square over delta R square plus 1 over 4 R square plus epsilon tilde G over R square plus 1 over R square delta square over delta phi square, where epsilon tilde is epsilon over Vf. So this equation then becomes, so we have to solve then. Let us take one of these. So let us deal with one of these equations. So we have R1j plus twice G epsilon R plus G square minus J into G minus 1 minus Ig over R square. So we have this non-Hermitian terms here. If you go through actually the hydrogen atom in this and follow the Sakurai book, actually, there is a non-Hermitian term there which has to be dealt with, and with redefining some of the variables there. So this is a general feature in this, even in the 3+1, you have such a situation there. So to deal with this, let me define then R1. Remember, it is a Coulomb-like problem. So you should be aware that in Coulomb-like problem you can make this transformation. Okay, then it reduces to actually this one. Plus 2G epsilon R minus J into J plus 1 over R square R1J equal to 0. So you are approaching very near to what we have a hydrogen atom here, J into J plus 1. Now this is to reduce this to the confluent hypergeometric equation. We make another transformation, R1j equal to Rj e raised to power minus I epsilon tilde r times g j. Then finally you get this equation. Gj plus twice j minus I epsilon tilde r plus g into r delta j over r minus twice ij epsilon r plus g equal to 0. Okay, so this is as far as I could go. Okay, this is a good problem for you to do, but I give you the reference why it is interesting, because people do this known as Coulomb impurity problem in graphene, and they have similar situation. So this is the treatment which I have, but there is a different treatment. So the idea is to calculate the local density of states by solving this equation, then calculate the local density of states, and this is a reference. In this reference the same problem is done, but in a slightly different fashion. Okay, so the reference is the Coulomb impurity problem. In graphene. So by VM, this is PR, PER, EIRA, J. Nilsson, and A.H. Castro, who actually wrote this long article in the Reviews of Modern Physics on graphene. Castro. So this is, the famous people are doing this, so I think you should probably, it is not a bad problem to do archive. I don't know whether it is published or not. 0706 2872 version 2. Okay, so you can do this. It was on 27 June. I haven't followed later on what has been done here, but I don't know whether this paper is published or not.
So J takes half integer values?
Yes. Which I wrote on J plus minus 1/2 3.
So, is there some physical significance to this minus IG?
Yes, it is. Actually, this problem arises even in this hydrogen atom. If you actually reduce it to the form which I have reduced, whenever you have the electric field, actually, because you see it traces back to alpha dot E in that, and it I alpha dot E, so it is there, and it is done in detail in Sakurai's book, actually, on advanced quantum mechanics, where he has done the hydrogen atom. Not the way where I was doing was actually just getting the exact solution, but he actually go through the way here has been done. That is in the approximations in the relativistic. It is not exact solution, but it is done, but it is very physically illuminating actually. And there also the non-Hermitian terms actually comes, and he deals with it in a way by making a transformation. This is a common problem actually whenever you do.
The fact that this is a relativistic equation, and that's why J doesn't take the value 0.
Yes.
The fact that this transformation, because if J takes the value 0, this transformation is not valid.
Yes. It is not. Yes, it is. Okay, now I come to my last thing, which in fact I am doing, and this is this may be boring, but this may be little more interesting. So now, for the first time, I will do now with the Lagrangian. So with the introduction which I gave you with the psi A and psi B field, let me write down the Lagrangian now. Equal to psi A bar I gamma mu psi A plus psi B bar I gamma mu delta mu psi B minus m bf times psi A bar psi A minus psi B bar psi. Remember the minus sign which comes there. Okay, where, as I said there, so these will give the Dirac equations which I wrote down previously. Psi A B are related by parity transformation. Just to remind you, psi B x. And if you want to write the Hamiltonian density, then it will be equal to Vf psi A bar minus I gamma I delta I psi A plus psi B minus I gamma I delta I psi B plus mf sigma f psi A bar psi B psi A minus psi B bar psi. Now this has what is known as conjugate symmetry. Again, you can see this in Semenoff paper which I gave you the reference previously. That is under psi A going to sigma 3 psi B H goes to minus H. Now you see this Lagrangian which I have wrote has a symmetry. It has a symmetry under the even the presence of the mass term, because you see these are separated here, not in the chiral one where we have psi L and psi R. So this has a symmetry, and this symmetry is so this Lagrangian is invariant. Our L is invariant under two independent global transformations, that is psi A goes to E alpha A, psi A, psi B goes to alpha B, psi B, even in the presence of, so invariance even in the presence of M.
This cannot be enlarged to a U2, or can it be?
It can be if you have another internal symmetry, but here we have only this one here.
Yeah, I mean, psi A, psi B, I consider them as a column vector distributed U2x.
Yes.
So can
yes.
it be enlarged to U2? Does this have U2 symmetry, this Lagrangian, or not?
I'm not sure, but it has this U1 cross U1 symmetry, but I'm not sure whether it has U2. There is additional symmetry it has. So this is invariant then under UA1 cross UB1. And since you have symmetry, you have two conservations, J mu psi A, gamma mu psi A, J B mu psi B, gamma mu psi B. Okay, so let me form even and odd combinations of this. So even and odd combination will be psi A, gamma mu psi A plus minus psi B, gamma mu psi B. And these combinations you can easily check. One will have one parity, the other will have other parity if you have that transformation there. Okay, so this is actually even in the masked present. Now, if you go to the 3 plus 1 dimensions, there we have the chiral symmetry, but the chiral symmetry was broken by the masked term here. Now this Lagrangian actually have other symmetries also, but those are in the absence of the masked term. Let me show you the other symmetries here. So we have no gamma 5 here. So no gamma 5. But we may generate chiral currents in the sense which I give you below. So inverted commas. Because if I consider these infinitesimal transformations, psi A B going to psi A B prime equal to psi A B plus I alpha psi B A. This B H, I am changing this. So this is one type of, and also I can have psi A B prime equal to psi A B plus minus, here also I have actually plus minus alpha psi B A. Then our Lagrangian will transform like this one. In the first one, it will be to this one, the term which is without mass, which is invariant, minus twice I m Vf alpha, then psi A, psi B, okay, minus psi B, psi A. So it will transform like this one. In the second one, we will have alpha equal to alpha 2 prime. This will be equal to again alpha. This minus twice m Vf psi A bar. This you can easily check, psi B plus psi B psi A. So the invariance here holds only if m equal to 0. Otherwise you don't have. So in the absence of the mass, we have then the currents here. So in the absence of the mass, so conserved then current, conserved chiral currents are actually J3 mu, and 1 is always there. Actually this I, that comes even here also with the plus sign here. That is like a vector current which is always there. So we have here 1/2 psi A bar gamma mu psi B plus psi B bar gamma mu psi A. And the other one, J5 mu, is minus I by 2 psi A bar gamma mu psi B minus psi B bar gamma mu psi A. Now this corresponds to actually for the to the, let's say, vector and axial vector in the even in the SU3 it will be exactly like that here. So let me write down actually the divergence of these currents in the which will be non-zero only in the presence of the mass. So this will be IMF psi A bar psi B minus psi B psi A, and delta mu m psi F psi A bar psi B plus m psi. So it is actually even under parity, and this is odd under parity if I have this one. So this is actually, if you remember in our 4 dimension, you have partial conservation of axial vector current, and which is in the quark model, if you have there and if it is the isospin current, for example, and if you have the quark model there, you will have this one as twice m the quark mass times u bar u d bar, and it is has the same type of thing here. we have, so it is an interesting possibility. Here you have an anomaly, as is well known in, and whether this current also develops an anomaly which is related to the current which I have introduced in the previous lecture. So let me go back to the previous lecture after this. So let me now introduce, as I have introduced the electromagnetism in the previous lecture, so I will not repeat it, and what I will see that we obtained the following equation there. So if I introduce the electromagnetism in the usual way, as I did previously. Okay, so then we had this equation du plus E over 2c sigma mu nu F mu nu plus V F square M square psi AB, where we worked out this one, E over 2c sigma mu nu F mu nu. We worked out this one as, there I called J lambda, here I am calling F lambda, where F lambda was E over 2c epsilon lambda mu nu F mu nu. Okay, so what is the Lagrangian here? The Lagrangian here, which gives rise to these two equations, will be so let me write here the Lagrangian will be psi bar A d mu plus M square V F square psi A minus psi B d mu M square V F square psi B plus we have this one minus psi B gamma mu psi B F mu. So this we have the Lagrangian here. So you see this is the current which I call J minus mu in the previous case. So this abnormal current here which we have here is actually coupled with this combination here, and which has also the opposite parity. And so this is actually in a way that the current to which this current is coupled is F mu. And its interpretation I leave to the seminar, but actually I am interested here whether this one actually develop an anomaly or not. And I have done some work here, but it is still, although I have written, but I haven't put it on the net. So this is an interesting problem, because let me give you why this is so. Because if you have in 3 plus 1 dimension, you have this one, J5 mu. This is well known. The chiral anomaly there is well known. Rho sigma F mu mu at rho sigma. This is well known chiral anomaly there. And if I just work it out, E square over 4 pi square E dot D. This is non-zero actually, even if you put m equal to 0. But in deriving this, actually you use m as a regulator. If you see, but in the end, the result does not depend on the quark model, and this is well known. It is due to these triangular type of graph here. So you have here the divergence, then the quarks here. These are the graphs which contribute to this anomaly. So this divergence involves the quark mass, and similarly the propagators involve the quark mass. This anomaly occurs only if you have one axial vector vertex at scalar vertex and two vector vertices. Otherwise, this anomaly is not there. And then if you work out this triangular graph, this is a famous one given by Adler, Fuss, and Jakovic. So this then equal to this. Whether there is a corresponding one here is an interesting question, and whether this, because you can write actually very easily, which I have written these Feynman rules for the field theory for the case of this 2 plus 1 dimension, and you have the Coulomb potential there. And then work out, for example, the polarization vector and things like that, just as you do in electrodynamics. So you can do that also. So I have done this, but I will put it somewhere later on. So this is all I wanted to tell you.
Questions? All right, let's thank you. And thank you so much for coming. And we will make these videos as well as the lecture notes available in due time. I'm not sure.